All right, today we're going to unlock a secret weapon of mathematics, the Euler method. We're going to see how a surprisingly simple trick helps us find answers to problems that, well, seem completely impossible to solve. Ready to see how it works? Let's dive in.
So imagine this. You're trying to predict the future path of a satellite or, say, the spread of a forest fire. You've got an equation that perfectly describes all the forces at play, but there's a huge catch. There is no way to solve it with a clean, simple formula. It's kind of like having a treasure map where the final destination, the X marks the spot, is just smudged out. What do?
Okay, so let's meet the specific kind of mathematical problem that forces us to get creative. This is the equation that's incredibly useful, but often, impossible to crack directly. We're talking about something called ordinary differential equations, or ODEs for short. Now that sounds super complex, I know, but it's really just the mathematical language of change. It describes everything from a cooling cup of coffee to the swinging of a pendulum. An ODE simply connects a value to the rate at which that value is changing. It's the how fast behind the what.
Now, while some ODEs are pretty simple to solve, a lot of them, like the one you see here, are total locked boxes. We can't solve them with standard methods, which means there's no clean y equals formula just waiting to be found. And the frustrating part, we know a solution, a curve, exists, we just can't write down its equation. So are we just stuck?
No way, not at all. This is where we pivot. If we can't find a single perfect formula for the entire solution, maybe we can find a different kind of answer, one that's built piece by piece.
You see, the new goal is to generate what's called a numerical solution. So instead of one elegant expression, we're going to create a list of coordinates, a set of points that lie really, really close to that true invisible curve. It's almost like creating a connect-the-dots puzzle that perfectly outlines the shape we're looking for. And this visualizes the strategy perfectly. We start at a point we know, B0. From there, we take a small, calculated step forward, a distance we call h, to find our next point, B1. Then we just repeat the process from B1 to find B2, and so on and so on. By stringing all these points together, we start to build an approximation of the real curve, one tiny step at a time. So the big question is, how do we actually calculate where that next point should be? This is where the genius of the 18th century mathematician Leonhard Euler comes in, with a method that is one of the oldest and, most beautifully simple ideas out there.
To take our first step, we need two key pieces of information. First, we have our starting point on the graph, that B0. And second, the differential equation itself tells us the slope of the curve at that exact point. So think of it like this. We know our exact position, and we have a compass telling us exactly which direction to head next.
And here it is, the beautifully simple idea. If you know where you are and which direction you're facing, just take a small step in that direction. Euler's method makes this powerful little assumption. For a very, very short distance, the curve basically behaves like a straight line following that initial slope.
And this formula right here, this is the engine that drives the whole method. Our new y position, y1, is just our old y position, y0, plus a tiny adjustment. And that adjustment is our step size h multiplied by the slope at our old position. So in plain English, it's new position equals old position plus a small step in the direction the curve is pointing. That's really all there is to it.
All right, enough with the theory. Let's see how this powerful little formula actually works with a real example. Let's get our hands dirty.
Okay, here's our mission. We've got our ODE. We have our starting point, when x is 0, y is 1. And our goal is to figure out the approximate value of y when x gets to 0.1. To do that, we're going to break the journey down into 5 small steps, which means each step, our h, is going to be 0.02 wide.
So we plug in our starting point of 0.1 to figure out the initial slope. We take our first step of 0.02 in that direction, and we land at our first approximation, y1 equals 1.02. Now, here's the key. We use that new point to calculate the next slope and take another step. It's like a chain reaction, where each new answer becomes the starting point for the next one, until we've done all 5 steps.
And there we have it. After 5 little jumps, our approximation for y at x equals 0.1 is 1.0928. We've taken an equation with no clean formula and actually managed to pull out a concrete numerical answer. We found the x on the smudged part of the map. But as you might have guessed, there is a catch. The very simplicity of Euler's method, Well, it's both its greatest strength and its greatest weakness.
Right here, we can see the fundamental trade-off. That's the true solution curve we're trying to find. The straight lines are our steps using Euler's method. And because the real curve is constantly bending, our straight line steps just can't help but drift a little further away from reality with each and every iteration. The error starts to pile up.
So the key takeaway here is that this is not a perfect tool. That error stacks up. If the real curve's slope changes really fast, our method, which assumes the slope is constant for each small step, can become wildly inaccurate. In some cases, the final answer can become, and I'm quoting here, completely useless.
But this doesn't make it any less important. Not at all. We have to remember that Euler's method is the foundation. It was the first simple, intuitive step in a long journey of developing much more complex and accurate numerical methods. You could say it's the ancestor from which all the other more powerful techniques grew.
And this leaves us with a fundamental question that goes way beyond mathematics. In engineering, in science, even in our daily lives, we constantly face this trade-off, don't we? Do we choose the simple, fast solution that's good enough, or do we go for the complex, difficult one that's more precise? The story of the Euler method shows us that sometimes the simplest first step isn't just a good starting point, it's the most revolutionary one of all.